Hey everyone, welcome back. This is the third lecture. It's a lecture about the simple regression model. Simple regression just refers to regression where you just have one predictor in the model. We'll talk about what this means in a little bit, but the idea is that there's only one predictor and one outcome. When it's more predictors than that, then we call it multiple regression. But this lecture is going to be all about the simple regression model, just one predictor variable. So to help you really understand what's happening in regression, it is really helpful to start with scatterplots. And here, each point represents a single observation. So each point on that plot is like a single person. And they have a score for the x variable and a score for the y variable. In a situation like this, the scores are pretty nicely distributed across them. We have just like a perfect sample. That's not always going to happen. But what's great is that regression is going to give us what's called the line of best fit. And here we have that shown with that red line. It's the line that best represents the data. We're going to define what that means in a moment. But that line happens to go through what's called the conditional means. And the conditional mean means it's the mean conditional on something else. Here, what we're saying is that it's the mean at each value of x. So if you have, let's say we're looking at x equals 1. The mean at x equals 1 of y is going to be like 2.5. The mean of y when x is 2 is 3. The mean of y when x is 3 is 3.5. The conditional means are just that. They're conditional on something else, but they're the mean of our outcome. I have them circled here on this plot. Each circle represents a conditional mean when x is at a different value. In this case, all the conditional means run perfectly along the line. This is what happens, or approximately happens, when we have an assumption field called linearity. We'll talk about that later. When the points really, the best fitting line truly is completely linear, then this is what is going to happen. What's also cool about that line is that the line is the linear models or the regression model. It's predicted level of y for each level of x. So with just two pieces of information, knowing x and y and this best fitting line that comes from those, we could say, well, if I just know someone's x score, we could have an idea of what their y score would be. So for example, if we had someone came in that had a score of 4. If we didn't know anything about their y-score, but we had this information, we had the best fitting line, we could guess what their score was. And in this case, we would say they probably are somewhere close to 4. So that line is what we would predict just knowing the predictor score. This is going to make more sense as we get further into it. But that line is a special line. It's a predicted level from the regression. It goes through the conditional means, and it best represents the data. So why is that line considered the best? Well, that line is the line that minimizes the error between the predicted values, what we predict for that person. So say a person that scores a 4 on the x, there's some people that didn't score a 4 on y. There was a person that scored a 2, a person that scored a 3, a person that scored a 4. So that one's perfect. But then there's a person that scored a 5 and a 6. So we're technically wrong. We have error where those points don't fall exactly along the line. A better term for that error, I think, is what's called the residual, because it doesn't mean your model is wrong. It just means that there's a difference between the predicted value and each point. And this is essentially always going to happen unless you have a variable that perfectly predicts another, which is usually not super useful in practice. So what we're going to call this is the residual. It's what's left over between what we predicted and where the points actually are, the observed points. This can be seen in this equation. The SS stands for the sums of squares. So this is the sums of squares of the residual, which is a good name for it because what we're talking about is we're going to sum up the squared deviations. So that first y value, the one without a hat on top of it, is the observed value. That's what's actually observed, what happened to that person. So if we're talking about the person that scored a 4 on X and scored a 3 on Y, their score for the Y would be 3 for that person. So YI stands for the observed value for each individual, every individual in there. The hat one is what we predict. So that's the line. And then we get the difference between those two and we square it. And we do that for each observation throughout the whole sample, and we sum them all up. You've seen something extremely similar and actually built on this in ANOVA, so hopefully this is a little bit of a review. But the idea is that we're taking the difference between what we would expect and what we actually see and summing all of those squared values up. Thus the term sums of squares. It's summing up the squared deviations from our predicted value and what we actually observed. This approach is called the ordinary least squares regression approach, or OLS. So that line is the line that makes the sums of squares residual as small as it possibly can with a straight line. No other line, you could draw a million other lines in there, and every line would be slightly bigger sums of squares than that line right there. That's what makes it the best fitting line. When we're actually calculating the best fitting line for simple regression, it's fairly straightforward. There's a lot of number crunching, but it's not difficult math. For our slope variable b1, that's telling us the slope of that line. In other words, if we move over 1 unit in x, how far up do we go in y? That's the slope. That equation right there gives us that slope. So it's the difference between the observed x and the mean of x. That's our first bracket, times the yi minus y bar, which is the mean of y and the observed value of y. So we have the observed x minus the mean of x, the observed y minus the mean of y, times each other, divided by what is actually the variability of x. It's the observed x minus the mean of x squared. In other words, it's the covariance of x and y divided by the variance of x. Covariance is just a fancy word for saying, do they move together? If x goes up, does y tend to go up? If x goes down, does y tend to go down? Or conversely, when x goes up, does y tend to go down? And then when x goes down, does y tend to go up? Both of those would be a covariance. They're covariant, they go together. What's awesome about this is that it's fairly straightforward. It's just saying how much they move together over how much does x just move anyway. That gives us our slope, and that is very interpretable. It is the slope of that line. So how much does it go up when you move over 1 unit in the x? The intercept is where the line crosses the 0 point of x. So it crosses that line, that 0 point. That's the intercept. So that tells us what is the average y value when x is 0. That's what the intercept means. And we use that equation there with the mean of y minus the slope times the mean of x. This is interesting because throughout all these equations, you see a lot of the means of x's and y's here. They're extremely important. This is going to come up as some of the assumptions come up later on, is if a mean doesn't really tell you much about a variable, For example, if you have a categorical variable, uh, then you have to make adjustments to make this work. And we're going to talk about what those adjustments can be. That last little bit right here, I'll hide myself, is the full line is represented by the intercept plus the slope times whatever the x observations are. That tells us the whole line. It's really interesting. Just knowing the x variable, what they scored on their x, and the intercept and slope, we can know exactly what the predicted line is. So the question becomes, if so much is riding on this line, we're doing a regression model so that we can find that line. Well, that line is actually generally what we're going to be interpreting, at least in a lot of cases. So how do we interpret that line then? Well, it's the value of the slope, that B1. It tells us the change in our predicted y associated with a 1 unit or 1 point increase in x. So if we increase somebody's x score by 1 unit, what would we expect to change for their y score? So I have an example here, just a quick one, where x is the number of days in quarantine, y is the number of episodes of bad reality TV watched, and our slope is 2. The interpretation for that is right below. It says, for each additional day spent in quarantine, that's for a 1 point increase in x, so it's a day. For each additional day spent in quarantine, there's an associated increase of 2 episodes of bad reality TV watched. That is, let's say I was spending 30 days and then I was going to spend another day. On average, I would increase my bad reality TV episodes watched by 2 episodes. Similarly, if we know the intercept and the slope, we can also produce values of the predicted value for new values of x within the data range. We don't ever want to predict outside of what our data actually have. For example, if we, for this quarantine example, if in our sample we have people that are in quarantine from 10 to 30 days, we don't want to predict what would happen to somebody on day 31 or 40 or 50 because we don't have information about that. That's called extrapolating. It's a dangerous game. Sometimes it's necessary, but often it's just going to show that you don't know what is actually going to happen. Anyway, back to this example. If we know the intercept and the slope, we can actually say exactly what the predicted value is for any value of x. For example, let's say our intercept is 0.5 and our slope was 2, like it was before. We can say, if we're on day 35, we can say, how many episodes do you think we've watched at this point? We can actually just fill in the value. So we have 0.5 plus 2 times whatever the x value is that we're at. So in this case, 35. When we actually do the math there, it equals 70.5. So about 71 episodes have been watched after 35 days of quarantine. I'm hoping this is making some sense. This is your first time really getting into this. I understand if it's a little bit confusing. Stay with me on this. We're going to get more and more examples. Another thing that's interesting about a regression model is that the residuals, what's left over, so the difference between the point and our predicted line, what I show on this graph where the difference between the line are those vertical red lines, it depends on minimizing the residuals, so they're obviously a big deal. The line is totally based on them. They're going to come up quite a bit. And when we think about the residuals, one thing we can think about is that there's three pieces of information in every observation that we see. So when someone comes in and we see what their Y score is and their X score, we can break out their outcome, their Y score, into three pieces. One is just the mean, the grand mean. That's just saying, on average, this is what people are like. That's already some information. The second piece is the explained component. This is the part that we're saying we actually understand why this predicted value is different than the mean. This is going to make more sense as we get further into it. But I want you to understand that that line tells us more information about an individual than just the mean did. So let's say we don't know much about anybody, but we have all their Y scores. Our best bet is to be able to say, okay, this is the mean. That's our best guess what someone knew coming in to the clinic, what their score would be. That's our best guess, is what is the mean. But if we have more information, let's say now we have their X score, we can do a little bit better than that. We don't have to just guess at the mean. We can now guess at the line. And this explained component is the model actually tells us why that individual would not be right at the mean. So on these really low values of X, we can see that people are going to be pretty low on Y. That is, we can say they're low on Y because they're low on X. The association tells us when you're low on X, you're more likely to be lower on Y. When you're really high on X, you're more likely to be higher on Y. So the model is already telling us a little bit more information about this individual than the mean would on its own. But what's left over is the unexplained part. The unexplained part is, why are these people not right where we predict them to be? Why are they not right at that line? For us, that remains a mystery for this model. We don't know why those individuals didn't score right at the mean. But because in the social sciences we're studying humans, humans are complicated. There's always going to be other factors that influence what their score is on some outcome. That means what is left over in these residuals is technically other things that are influencing Y. So it could be age, it could be sex, it could be experience, it could be education. All of these things are also influencing Y, and all we have here is X explaining Y. So there's still more, and that's why there's some left over, this unexplained component, because our model doesn't explain it yet. We could, and we're going to talk about this in the next lecture, we could add more variables to it, which would then help reduce the residuals, because we'd be able to explain more and more about those individuals, and there'd be less that we can't explain. Again, the explained component is the difference between the mean and the predicted portion. We know why that happens, because there's a relationship between X and Y. We can say this person on this very far left that scored pretty low on Y and scored really low on X, we can say we expected them to score lower than the mean because they scored low on the X. They didn't score exactly where we expected, but they did score lower than the mean exactly as we expected from the explained component of the model. Hopefully this is making some sense. So every model is basically breaking up the observed values into three parts: the mean for everybody, the explained component, how much we can explain where they differ from the mean. Why do they differ from the mean? And then the unexplained part, why do they differ from the predicted line? A few things to know about the residuals because they're really important. The mean is always exactly 0. So if you just take the mean of your residuals, it's going to be exactly 0. That is just how it is in a regression model. What's maybe more interesting if you're into stats is that the correlation between the residuals and your predictor is exactly 0. And you can take a second to think about why would the correlation of the residuals with the predictor be 0 every time? If you remember, I said that the residual is everything left over that X can't explain. It's everything left over. So it's all the stuff that X doesn't tell us about. That is, it's all the stuff that has nothing to do with X, so the correlation is going to be 0 with that stuff. So the last piece that I really want to cover is the variance piece. The variance of the residual, that tells us basically how big the residuals still are. How much are we not explaining and why? The variance of our residuals is termed this bar y dot x, and it's equal to the variance of y times 1 minus this r squared value. The r squared value is the proportion of variance in y explained by x. So the 1 minus the r squared is the proportion of variance in y not explained by x. That number is always going to be 1 or smaller. That is, the variance of the residuals will always be equal to the variance of y or smaller than that. The more and more that we explain in y, the smaller the residual variance is going to get. So again, the r squared value is the proportion of variance in y explained by x. How much of y does x tell us about? So besides being important for us to find that special line, residuals also tell us other stuff. Residuals help us understand partial relationships. That is, when we control for stuff, what is the effect of x on y? This actually helps us do some causal inference, which is going to be important and relates back to the previous lecture. There's also residual analysis to detect anomalies. Sometimes there's points in the data that are going to be really hard to know are weird until you look at the residuals. And then you're going to be able to see, whoa, there's some strange cases in this data, and you can go investigate those more fully. It also helps you detect nonlinearities. So there's going to be times where the relationship between x and y is not linear. The line doesn't represent it very well. When that happens, the residuals can help us see that. It also is going to help us assess a homoscedasticity assumption. I know, say that one fast, right? So homoscedasticity is this idea that the variance of the residuals is basically the same across the whole line. It doesn't fan out in one direction or another, which we'll talk about in a lot of depth in Unit 2. All of this information comes from the residuals. Without the residuals, we wouldn't know how good our model is. We wouldn't know if it was significant. We wouldn't know any of that stuff. Speaking of significance, how do we know that something is significant? What we're actually going to be using is, of course, the residuals. We're going to use the standard deviation over the residuals divided by the total sums of squares of x. That's going to give us the standard error of our slope. And then we're going to do the slope divided by the standard error of the slope, and that's going to give us a t-value. Not very different from what we've already done in previous statistical courses. We're going to compare that t-statistic to the t-distribution to get a p-value. And then typically that p less than 0.05 indicates statistical significance. So this isn't going to be entirely new. It's very, very similar to what we've done before. But now we're going to get more information. There's going to be more things that we can interpret that we can see if it's significant or not. We're going to talk a lot more about this and effect sizes in Unit 3. When we're actually in R, this is what it looks like. We're going to run a model. I'm not showing the code yet. But the output looks just like this, where we have speed is predicting the outcome, which is distance in this case. And this is using this fake cars data that comes with, maybe it's not fake, it might be real, but it's just this example data set in R. And what this is saying is speed, that line that has speed, and then the boxes where I've highlighted the 3.9 and the 0.41. The 3.9 is the estimate. That's the coefficient or the slope. The standard error is the standard error of the slope. The t-value is the estimate divided by the standard error. And then we get our p-value, which is really, really small. That e to the negative 12 means that we move that decimal point over to the left 12 times. So it's 0.00000011 times to 1. So it's really, really small. So what does all this mean? Well, in this context, it means that the speed variable significantly is related to distance, the outcome. We can actually interpret that 3.9 directly. We can say for every 1 unit increase in speed, there's a 3.9 unit increase in distance. So I'll say that again. For a 1 unit increase in speed, there's a 3.9 unit increase in distance on average. And that's significant. So we'd expect to see that in the broader population, that there is an effect out there. Let's try another example. Because it's 2020 and the quarantine's been going on, it's a weird year, we're going to use this example. You've been super bored during quarantine and have been binge watching The Office and Parks and Rec to try and pass the time. This is actually pretty accurate of me. As you become increasingly stir crazy, you decide to create a data set based on these sitcom characters and some of their traits, because why not? After compiling the data, you want to see, and this is a research question, if you can predict a character's income based on how awkward they are. Let's also say that you've somehow come up with this really valid metric of awkwardness, and it's a continuous variable. So in this framework, we're going to say the null hypothesis, the thing that says there's nothing going on, is going to say the character's awkwardness does not predict income. They're not related. The alternative hypothesis is going to say the character's awkwardness is a significant predictor of income, or they are related. So first thing, I always recommend when you're doing any statistical analysis, look at your data in a graph. A scatter plot is a great way to visualize it. Here we're looking at awkwardness across the x-axis and yearly income in thousands on the y. If you were to kind of squint and draw a line here, you'd see that there's kind of a negative relationship that as you get more awkward, you tend to earn less money. We've run the regression in R, and so we're predicting income from awkwardness. And our variable here, awkward, is saying there is a negative relationship because the estimate is negative 1.9. And if we go over to the p-value, we see that it is significant. With that in mind, how would you interpret that information? Well, if we look at the estimate, it's negative 1.9. So we would say for a 1 unit increase in awkwardness, we would expect a negative 1.9 unit decrease or lower income, and that effect is significant. Another way of saying that is if we increase awkwardness by 1 unit, we'd expect income to go down by almost $2,000 because income is in thousands, which tells us quite a bit. If we go up in awkwardness just a little bit, we're going to be losing roughly $2,000 a year for just a 1 unit increase. So if we increase 5 units, so 1, 2, 3, 4, 5, we can say we'd be missing out on $10,000 a year. And the effect is significant, which tells us we would expect to see this effect in the population if we had all the data. If we took data on everybody working and got their awkwardness and their income, we would expect there to be a negative relationship out there, somewhere around negative 1.9. The other thing that we have boxed here is the adjusted R squared. It's like the R squared that we talked about a little bit ago. It's a proportion of variance explained in the outcome by the predictor. But the adjusted adjusts for the complexity of the model, and it usually is what we would actually see in the population. So it's a great one to go with. The adjusted R squared here is 0.3878, so roughly 0.39. How we could interpret that is that awkwardness explains 39% of the variability in income. That means awkwardness alone is explaining quite a bit of why people differ in income level. This slide again goes over what I just said. Hopefully this is starting to make sense. That estimate in the slide, sorry, this one got messed up. The output should look like this. The interpretations are right here for us. For each 1 unit increase in the awkwardness, there's an associated $1,931 decrease in yearly income, and awkwardness accounts for 38.78% of the variance in income. I'm really hitting on this hard because this is going to come up the whole class. This is one of the core concepts I want you to take away from this course, is how to interpret that output. If it's not making sense to you, make sure you reach out. And now that we've run the model, we can look at the residuals to find out more about how things look. We want to understand, do things look really weird with the residuals? We're going to talk about this a lot more when we talk about assumptions. But the residuals, again, are what were observed, what actually happened to these people. So this person way at the top of the awkwardness scale, they have an income of like 19,000. No, like 10,000. Yeah, 10,000. You have where it's predicted is roughly 25, 30-ish. The residual is the difference between what they actually earn, their real income, and what we would predict. And these residuals we'll use later on for a lot of stuff. Really, one more thing about regression. Regression got its name from what's called regression to the mean. It's a phenomenon that exists in just about everything. It's the idea that extreme values in one variable are often associated with values closer to the mean in another variable. So I'm showing 2 lines on here. If regression to the mean didn't actually happen in reality, the line that goes right through those points, the expected if no regression to the mean, would be the best fitting line. But in reality, that doesn't happen. So we have this example right here, where we have the father's height in inches and the son's height. And what you're seeing is a father that is really tall, 75 inches. On average, their sons are actually more like 71 inches tall. They're not 75 inches or taller. Rather, they're 71 inches. So an extreme case where someone's really tall, 75 inches tall, their children are more likely to be closer to the mean or regress to the mean than they are to be as extreme as they are. They're still taller on average, but they're not as extreme as the father. And you see that also when you go on really low values. So really short fathers tend to have sons that are not as short. Right in the middle, you actually see a balance where if you're right at the mean of your variable, the distribution, then you tend to also have individuals like your son's height would be right at the mean, roughly. But you do notice that there's a lot of variability around this. So even at the highest, where the father is 75 inches tall, you do see that some sons are 75 inches tall. That doesn't say that it's not a possibility or not going to happen sometimes or even often. But on average, they're going to be shorter. And that is where regression got its name. It's because that line represents the regression to the mean line. So why talk about regression to the mean? Well, first, it has implications for difference scores. For one thing, when you are looking at did someone improve from pre-test to post-test, and you're looking at the difference between those scores, generally you're going to need to control for the initial scores of covariate. You want to control for pre-test scores. That actually helps us understand what the regression to the mean looks like. It helps us control for that phenomenon. Regression, when used right, naturally accounts for regression to the mean, which is really nice. So we don't have to worry about regression to the mean. We're not concerned like, oh, we had some really low cases and really high cases, because regression is going to account for those naturally. We need to interpret results where extreme values are associated with more average scores with caution. We don't want to say, oh, people that are really tall, like their genetics run out and they have shorter kids. No, it's just the way of life. It's not anything about their genetics changing. For example, what you often see with regression to the mean, so you'll have what's called the curse of the cover page. It's where individuals are having a really good year in sports. They make it to the cover page of like Sports Illustrated, and then they don't seem to do as well after that. And a lot of people are like, well, pressure got to them. It was just too much. There was too much hype. But it turns out when people are doing super, super well, they're actually doing a lot better than what they normally do on average. And so just by chance, just because life is the way it is, over time, they're going to come back down to more their average level. They may improve over time, but it's not going to be as drastic as it may have looked to begin with. So we don't want to give a lot of meaning to the situations where individuals do regress to the mean. It's just going to happen. An aside, looking at a difference score with the first score as a covariate, so looking at how much did they improve from pretest to post-test as the outcome and controlling for pretest, or using the second, so the post-test as the dependent variable or the outcome and controlling for pretest, they're actually identical in meaning. You'll get the same results for the slopes. I think that's really intriguing. So regardless of using a difference score or just the post-test as your outcome, when you're controlling for the pretest score, either way is going to work just fine. That's really just an aside. Nothing we're talking about in depth yet, but just to have on your radar. Last thing, if you want to get more practice, these are really great resources to give you some practice outside of class. They're free, they're just available online. check them out when you get a chance. And that is it for this first real introduction to regression. Reach out if you have questions. We're going to next discuss about multiple regression. We're really just going to build on the ideas that we shared today. And hopefully a lot of these things will become more and more concrete as you get more experience with it.